Now we've got all the tools necessary to determine what the voltage and current along the transmission line and at the load are going to be when we connect a T-line and a load to some sort of generator with some sort of source. And I'm going to start solving this circuit here generically. And I'm going to go through all the steps, kind of summarizing what we've done since the beginning of the transmission line lectures. One of the first things that we were able to do was that we were to show that if we want to write the phasor voltage as a function of distance along the transmission line, we could write that in terms of what we call a forward wave, or a incident voltage wave, which we called V bar plus, and we knew at the load there was some sort of reflection that occurs there, and we called that V bar minus. And the voltage along the lengths of the transmission line is a summation of those two components. And specifically, we say that the voltage along the length of the transmission line is equal to the incident voltage wave, V bar plus, and it's got a sinusoidal component, e to the minus gamma z, where gamma is the complex propagation constant, alpha plus j beta. And then there was this reflected wave, which had a magnitude and an angle of its own, V bar minus, and it traveled from the right-hand side of the transmission line to the left-hand side of the transmission line, so it had a cosine term of e to the plus gamma z. So forward traveling voltage wave with magnitude and angle of V bar plus, and a reverse traveling voltage wave with magnitude and angle of V bar minus. And we developed a similar equation for the current along the transmission line. It was I bar plus e to the minus gamma z plus I bar minus e to the plus gamma z. And we see that the voltage and current waves have to have the same wave number and attenuation constant associated with them. They do not, however, have to have the same magnitude and phase. There can be phase shift along the transmission line because, remember, this is a complex number here. It has a magnitude and an angle associated with it. So the first thing we did is that we, after completing this, is that we were able to determine a relationship between the magnitude and angle of the incident voltage wave and the reflected voltage wave. And we said that that relationship is quantified by a parameter called the reflection coefficient at the load, and it is equal to the V bar minus to V bar plus, the ratio of V bar minus to V bar plus. And what this allowed us to do was substitute into this equation and write the voltage equation for voltage along the transmission line, and we were able to eliminate this V bar minus term. We'll write V bar plus e to the minus, not plus e to the V bar plus times e to the minus gamma z plus V bar minus over V bar plus e to the plus gamma z. And if we were to factor out a V bar plus from this equation, what that allows us to do is write it as V of z is equal to V bar plus times e to the minus gamma z plus the reflection coefficient at the load, e to the gamma z. And this was handy because we also have other formulas for the reflection coefficient that aren't dependent on voltage and current. They're only dependent on known quantities Z0 and ZL. So we can determine reflection coefficient. So that allows us to simplify this equation a little bit. And we could write a similar equation for the current reflection coefficient. It's V of, clearly not V, it's I of Z, is equal to I bar plus e to the minus gamma z minus the reflection coefficient at the load, e to the gamma z. And this just takes into account the fact that the voltage reflection coefficient and the current reflection coefficient are opposite one another. So we've got those two that kind of came from the same place. The next thing that we can do is we can apply a boundary condition at the input end of the transmission line, and we calculated what we called the input impedance. So we said, all right, well, how long is this transmission line, and what does that make this whole circuit look like in terms of impedance? And we can also, at this point, define the voltage at the input end of the transmission line, and we're going to call it Vin. So if we were to write a equation for Vn, it is going to be a phasor. So Vn, we no longer have to write of z because, well, there is only one Vn. It's the voltage V of z equal to whatever the length of the transmission line is. Sorry, minus L, because remember this is 0 and this is minus L. And if we were to replace this whole circuit with its input impedance, we could see that the input voltage has to be found through the application of a voltage divider. So we would say that Vn, it's the voltage at the input end of the transmission line. It is also equal to whatever the source voltage is, VSS, of our generator, times this Zn over Zn plus Zs. So we've got this input voltage to our transmission line can be found from this voltage divider formula. So we would just write V of Z equals minus L equals VSS times Zn over Zn plus Zs. So what we want to do now is plug this equation here into this, and we can say that this is a little longer, so I'm going to start over here. V bar in is equal to V of Z equals minus L is equal to, we just want to plug in minus L for the Z's here, so that's going to be V bar plus times E to the minus gamma minus L is just plus gamma L plus the reflection coefficient at the load times E to the gamma times minus L, which is just E to the minus gamma L. And that is going to be equal to this. Z, the voltage divider. And what this allows us to do is solve for V bar plus, since this equation here is equal to this equation here, since they are both the input. They're just different equations for the input impedance. So we can just now write V bar plus is equal to VSS times Zn over Zn plus Zs times 1 divided by this here, E plus gamma L plus the reflection coefficient at the load, E to the minus gamma L. So this is really a really important result. We can now find the magnitude and the angle of the incident voltage wave from the source voltage, the input impedance of the transmission line, the source impedance of the source, and the complex propagation constant, length, and reflection coefficient of the transmission line circuit, all of which we know how to solve for. So now we can figure out what this V bar plus is. So if we were to plug this back into this equation here, we could see basically where we're trying to get to is that V of Z is equal to V bar plus, which is just VSS Zn over Zn plus Zs times 1 over E to the plus gamma L plus the reflection coefficient at the load, E to the minus gamma L. So all this term here represents V bar plus, and then we need to multiply it by this, which is E to the minus gamma Z plus the reflection coefficient at the load, E to the plus gamma Z. And so that's V bar plus, and then this is the two sinusoids, forward sinusoids and the reverse sinusoid, sinusoid. And so this gives us our complete solution for voltage along the transmission line at any point, including the load and the input end. This application of this one can be a little tricky. The thing to remember is that L there is the specific length of the transmission line, right? That's how long the T line is here, and Z is still an independent variable in this case. It's still part of the phasor voltage, so don't confuse those two. Another thing that I see a lot of times that students will mistake is that because of this math that we did up here, the signs on the exponents flipped down here, and the plus gamma L is on the first term, and the minus gamma L gets multiplied by the reflection coefficient term, and that's not the case normally, right? So those signs are different than those signs. So be careful and make note of that.